Hello everyone, I'm Pravein from IBM Research India. Today I'll be presenting our work on debugging transient faults in data center networks using synchronized network-wide packet histories. This work was done along with Nishant, Raj, and Professor Manchun Chan at National University of Singapore. Cloud reliability is critical with several businesses and services relying on them, especially video conferencing these days. These cloud services are supported by data center networks at the scale of several thousands of devices with complex interconnects. Failures in these cases are extremely sensitive and can result in hurting the customer's revenues and incur a huge loss for the cloud providers. Data center operators have noted that most of the outages are caused due to network failures, and among the network failures, relatively large proportion, that is 29% of these failures, go without establishing the root cause. It was further observed that the failures that could not be root caused were transient in nature, and the debugging information, which is collected at different parts of the network, could not give a complete picture to correlate events leading up to the network fault. One such example of a transient network fault is microbursts, which are periods of high network utilization lasting a few microseconds. It has been found that such issues in fact encompass most congestion events in the network. Now, the reason of microburst could be due to a synchronized incast traffic when multiple hosts send traffic to a single host in a synchronized fashion, as shown in this example. However, it could also be due to network queuing, due to load imbalance, or heavy hitters, or network misconfigurations, and so on. So, to establish the right root cause of a network fault, the main question is, what capabilities do we need from the network? First is visibility, that is, network-wide and fine-grained visibility into each part of the network. Second is retrospection, that is, we need to know the exact sequence of events that happened before the fault occurred to be able to find the root cause of the fault. And third is correlation, that is, ability to correlate different events happening in different parts of the network. First, let's look at visibility and retrospection. To address the issue of visibility and retrospection, with programmable switches, there have been approaches such as per packet postcards or INTXD, where for each data packet, a control packet containing the packet's header information is created by the switches and sent to a central controller. This way, you have all the information before a fault occurs. However, the main problem with this approach is that there is a bottleneck due to limited network bandwidth available for exporting the postcards and the storage overheads, which cannot scale to several terabits per second. A diametrically opposite approach would be to append telemetry information in the packet headers in the data plane itself, as done by INT. This approach uses selective hosts to store the per packet telemetry information after extracting the headers. However, the main problem with this approach is that due to the information embedded in the data packets itself, it reduces the goodput of the network by up to 20%. Nevertheless, collection of telemetry information continuously in an operational network may be wasteful as the network faults occur very infrequently. Hence, it's actually possible to collect the telemetry information after a fault has been detected. However, such a reactive approach would miss out on the retrospection aspect, that is the historical information required for finding the root cause, especially in the case of hard to reproduce transient faults. So, how do we solve this problem of getting the visibility and retrospection from the network? By leveraging programmable switches, we record packets as a compressed packet records with telemetry information inside the switch memory itself. Next, since we cannot afford to flush the recorded data continuously all the time due to the overheads involved, as previously mentioned, we design a fault detection system in the network data plane to selectively export the recorded history to the controller for further debugging. Finally, we need to correlate the packet records at high resolution. For this purpose, we leverage recent data plane time synchronization protocols, which provide nanosecond level time synchronization between the data plane clocks of the switches. Hence, global time is available in the switch data plane while maintaining the packet records. With these three complementing techniques covering visibility, retrospection, and correlation, we develop synchronized network debugger, that is SYNDB. Now let me go into the details of our solution. In SYNDB, the switch data plane clocks are synchronized using the recent data plane time synchronization protocol called DPTP. Each switch maintains a recording ring buffer which compresses and stores the packet records, which we call as P records, upon reception of a packet. A P record typically contains the hash of a packet header, the time it enters the switch, and amount of time it queued in the switch. Additionally, it can also contain custom statistics that can be configured by the network operator. Let's say ingress port from which the packet came from. The key idea is to leverage the switch data plane as a fast temporal storage to do continuous recording of packet records as a moving time window. When no network fault is detected, the recording window moves ahead and the older packet records beyond the record time length are discarded. Hence, this ring buffer always maintains a recent history of events or packets. Next, the history of P records is needed when a network fault occurs. To do this, SYNDB allows network operators to program custom fault trigger conditions. For example, the operator could configure the trigger to be a high queuing delay for packets. Now, during network operation, let's consider a synchronized fan in traffic from many hosts to a single host, thus causing incast and leading to a congestion at switch S7. Upon the trigger condition hit at switch S7, it notifies all the switches and the switches in the network freeze a ring buffer. Now the collection happens individually in each switch and the P records are evicted and sent to a central collector via the control plane channel without affecting the data plane traffic. Now since timestamp is attached to each and every P record, collection can be performed out of order and the collector can easily reorder them in future. The P records are received by the collector, which then processes, orders them, and eventually stores them in a relation database, which allows the operators to perform network-wide queries. Now, after the microburst is detected, the operator can look at the packet distribution at S7 using the queries, and they would notice just equal distribution of packets at switch S7 from different hosts. Hence, in this case, local information is not sufficient to debug the root cause of this microburst. However, with SYNDB, since we have the ability to retrospect network-wide packet records, to determine if this issue of microburst is caused due to synchronized fan in traffic, a query of queuing delay at S7 together with the packet arrival information at the TOR switches before the microburst detection can be performed. Here, this top plot in this figure illustrates the queue buildup over time, and the bottom plot shows the packet arrival information of the host at the respective TOR switches. When we correlate the packet arrivals from different hosts before the burst occurred, we see that the packets that make up the burst are transmitted by host H1 to H6 at about the same time in a synchronized fashion. This way, the root cause of this incast from H1 to H6 can be determined and appropriate measures can be taken. Now, during regular network operation, we design a SYNDB runtime which provides network operators an interface to configure the statistics to be recorded in the packet records and to customize the fault trigger conditions. This configuration is initially used to generate a P4 program to be programmed in the network data plane. And this configuration can be changed at runtime without recompiling the network program. Please refer to the paper for further details on the runtime. Now let me go into the implementation and evaluation of SYNDB. We have implemented SYNDB on a mini testbed using barefoot Tofino switches over P4 and this runtime using Rust. Now using the mini testbed, we have evaluated the consistency of capture of P records in the data plane and additionally debugging of certain faults like microbursts as explained previously and network misconfiguration and so on. Additionally, we have also implemented a packet level simulator to understand the retrospection and correlation capabilities of SYNDB on a bigger network. Based on our simulation, we study how much of end-to-end packet history can be recorded by SYNDB in a large data center network with realistic workloads based on data center measurements. We observed that SYNDB could capture 4 milliseconds to 11 milliseconds of history from across the ends of the network for a network fault, depending on where the trigger occurs, whether it's in the destination TOR or the core of the network. Now, this is equivalent to hundreds of RTTs of history for packet level debugging for a network fault. And to get this amount of history, we observe that SYNDB utilizes about 5 to 7 MB of SRAM on an average per switch to maintain the P records. With recent switches supporting several tens of MBs and up to a few hundreds of MBs of SRAM, SYNDB can be implemented on current switches to support this amount of history for debugging. Hence, to conclude, we design and implement SYNDB, which is the first packet-level synchronized monitoring framework for the entire network. SYNDB can be implemented in existing switches and support hundreds of RTTs for debugging. Since SYNDB exports packet histories only upon network faults, it saves a magnitude of network faults, network overhead at line rate. Thank you for listening to my talk. Our simulator code is available at the given link, and please refer to the paper for further details and interesting use cases of SYNDB.